Language is a fascinating construct that allows human beings to communicate complex ideas and emotions. It evolves throughout our lives and plays a crucial role in shaping our thoughts and understanding of the world. Today, we're going to delve into how we can represent text for artificial intelligence, hesitating a bit, particularly when building agents with Python. We'll explore the various techniques and methodologies used to process and comprehend textual information. So, let's get started. Now, let's implement the installation of the GenSim library, which is essential for creating our word embedding model. First, we'll execute the command to install GenSim, ensuring this library is available for our project. Next, we need to import the necessary packages from both GenSim and NLTK, which will assist us in processing and tokenizing our text data. To begin, let's download the Punct tokenizer from NLTK, which helps us break the text into individual words. Following this, we'll define a sample dataset of sentences that showcase how language is used in different contexts. Now that we have our text data, we can tokenize it using nltk.wordTokenizing, converting each sentence into a collection of lowercase words. This step is crucial as it prepares our text for the Word2Vec model. After tokenization, we'll create the Word2Vec model using the processed sentences, specifying parameters such as vector size, which determines the dimensionality of the word vectors. Finally, we can obtain the vector representation of a specific word, language, from our model and print it. This vector encapsulates the semantic meaning of the word in relation to its usage in the provided context, paving the way for further AI tasks where understanding language is crucial. Now, let's implement the Bag of Words, or BOW, model using Python, which simplifies text representation by mapping documents into a matrix where the rows correspond to each document and the columns represent unique words from our corpus. First, we'll need to install the scikit-learn library if it hasn't been installed yet, because it provides the count vectorizer class that we'll use for this purpose. Next, we'll define a set of sample documents to analyze. These will be sentences related to language and AI. With our count vectorizer instance created, we will fit and transform our documents, which converts them into a BOW representation. During this process, the method captures the frequency of each word in the documents, resulting in a sparse matrix where each entry signifies how many times a word appears in a particular document. Finally, we convert this sparse matrix to a NumPy array for better accessibility, which we can then print alongside the feature names to demonstrate the unique words identified in our dataset. This method effectively prepares our text data for subsequent analysis or further machine learning tasks. Now, let's implement the term frequency, inverse document frequency, or TF-IDF model, which helps us enhance our text representation by weighing the importance of words in relation to the entire document corpus. First, we need to import the TF-IDF vectorizer class from the skylearn.featureExtraction.txt module. Then, we'll create an instance of this TF-IDF vectorizer, which will transform our sample documents into their TF-IDF representation. Next, we fit the TF-IDF vectorizer model to our document set by calling the fit-transform method on our defined documents. This step computes the TF-IDF scores for each word in the corpus, enabling us to understand which words carry more weight compared to others. The output is packaged in a matrix format, where each row corresponds to a document and each column reflects the representation of individual terms. Pretty neat, right? To visualize these results, we convert the TF-IDF matrix into a NumPy array using the toArray method, and print it out to see the numerical representation of each document. Additionally, we can retrieve and display the names of the features, those words that make up our matrix, by invoking the getFeatureNamesOut method. This approach not only quantifies the text, but also gives us valuable insights into which terms are crucial for document classification and clustering tasks. The chart, titled Text Representation Techniques in AI, shows 6 methods on the x-axis, including one-hot encoding, bag of words, TF-IDF, word embeddings, RNNs, and transformers. The y-axis represents the number of discussions scaled from 0 to 50, with numeric labels above each bar. The raw counts indicate one-hot encoding at 15, bag of words at 30, TF-IDF at 24, word embeddings at 35, RNNs at 18, and transformers leading at 40. It's quite interesting to see the key patterns emerge immediately. Transformers take the lead at 40, followed closely by word embeddings at 35 and bag of words at 30. Meanwhile, TF-IDF and RNNs sit a bit lower at 24 and 18, and one-hot encoding trails behind at 15. The height of these bars and the gaps between them, like the 5-unit gap between transformers and word embeddings and a 6-unit gap between bag of words and TF-IDF, show that there's a significant focus on transformer and embedding-based approaches compared to those classical count-based or simpler encoding methods. From what we can gather, contemporary discussions really emphasize contextual, dense representations, especially when it comes to transformers and embeddings, while those traditional methods still hold some relevance, albeit with fewer mentions overall. Now, let's implement a simple RNN model for text processing using TensorFlow and Keras. We begin by importing the necessary modules, including NumPy and the various layers from Keras. First, we define a sample dataset made up of a few short sentences that we'll use to demonstrate the RNN's capabilities. Next, we need to pre-process our text data by tokenizing it, which means converting it into a numerical format that the RNN can understand. For this, we'll utilize Keras's Packer tokenizer, which helps us fit our sequences and encode the text accordingly. Now, to ensure that all input sequences have a uniform length, we apply the pad sequences function, which is a crucial step for maintaining consistency in RNN input. So, let's define the architecture of our RNN model. We start with an embedding layer, which transforms our input integers into dense vectors of a fixed size, allowing us to capture those all-important word relationships. Following that, we use a simple RNN layer that processes the sequential input. And finally, we add a dense output layer with a sigmoid activation function to produce those binary predictions we need. After setting up the model, we compile it using the Atom optimizer and binary cross-entropy loss, which is what we often use for binary classification tasks. So, let's wrap up by displaying a summary of the model. This way, we can inspect its architecture and confirm that it's correctly configured for our upcoming training phase. Now, let's implement the following code to utilize a pre-trained BERT model for our text classification task. First, we need to import the necessary components from the Transformers library. We'll use BERT tokenizer for encoding our text and BERT for sequence classification to leverage the pre-trained BERT model optimized for classification tasks. Don't forget to also import Torch, which is essential for working with tensor data in PyTorch. After loading the tokenizer and the model, we create a sample text input that we want to classify. Next, we use the tokenizer to encode this text, ensuring it's properly formatted for BERT. This encoding process involves generating token IDs and applying padding where necessary to maintain uniform input sizes for the model. Once we have our encoded inputs, we proceed to make predictions. By surrounding the prediction code with torch.nograd, we ensure that the computation graph is not tracked, which saves memory and speeds up processing since we don't need gradients during inference. The model will return logits, Those are the raw prediction scores for each class. Finally, we utilize torch.argmax to determine the class with the highest score, then print the predicted class. This structured approach really highlights BERT's capability to effectively classify text based on its contextual understanding. Now, let's implement k-fold cross-validation, a technique that really enhances our model's reliability by evaluating it on different subsets of the dataset. We start by importing the necessary libraries, like kfold from sklearn.model-selection, which helps us split the data, and classification report for checking our performance metrics. In our example, we prepare a sample dataset, X, which is made up of textual representations, and we've got the corresponding binary labels stored in Y. The next step is to initialize our k-fold cross-validation with n-splits equals 3. This means we're dividing our data into 3 parts for training and testing. As we iterate through those splits, we'll retrieve the indices for the training and testing sets using kf.splitx. So, we create our training and testing subsets where xtrain and ytrain hold the training data, while xtest and ytest contain the evaluation data. Once we have these splits, we can dive into the training and evaluation logic, allowing us to assess our model's performance in a robust manner. Ultimately, we wrap things up with a simple print statement indicating that model evaluation is complete, encapsulating a vital step in ensuring our model's effectiveness at understanding those nuanced aspects of language. Today, we're diving into the fascinating world of how we represent text for artificial intelligence. We'll explore everything from word embeddings to those advanced transformer architectures. These are the building blocks of how machines make sense of our language. It's pretty amazing when you think about it. By developing AI agents that can process, comprehend, and just genuinely interact with human language, we really do open up a whole new realm of possibilities. I mean, we're talking everything from chatbots that can hold conversations to automating the creation of content and so much more. As technology marches forward, mastering these concepts is going to be crucial for shaping the future of how we interact with AI and each other. So, thanks for joining me on this journey.